Hello everyone, welcome back to my channel. My name is Cha Cha, and today I'm going to be going over the second chapter of the Chemistry Kaplan textbook, which is the periodic table. Bum, bum, bum. Before we get started, just one thing I want to say is that I am a student myself, so there may be mistakes in this video, and I apologize ahead of time if there are. But if there are, please let me know in the comments because, like you, I'm studying for the MCAT and I want to get a good score. I can't do that if I make stupid mistakes. Um, I should say preventable. Uh, so I took this periodic table from Google, just like online if you search up periodic table on the MCAT. This is what is the first option. So real first, let's get us orientated to what the periodic table is. So up and down are the group slash column. They're interchangeable names, and then from left to right is a row slash period. Um, in the first column or group, you have alkali metals, which are really reactive because they have one valence electron. Because they have one valence electron, that means that they will do anything to complete their octet, or to lose that electron. Then we have alkaline earth metals, still reactive, not as reactive as alkali metals. Then you have your transition metals, which is kind of like this 10 block stretch here. Then you have metalloids, which kind of start from boron, and then it goes like right one, right one, down one. And kind of on either side, those are kind of the metalloids. And I'll explain a little bit further what metalloids are. Then you have chalcogens, which have six valence electrons, so they're reactive, not as much as halogens, because halogens have seven valence electrons and they're really close to completing their octet. Noble gases aren't reactive at all because they already have their octet. They don't want to lose electrons or gain electrons because that will throw them out of balance. Um, then you kind of have like the black sheep that aren't really talked about as much on the MCAT is the lanthanides and actinides. So elements are grouped together based on their valence electrons. This tells basically how stable slash reactive an element is. And I was saying noble gases are super stable because they have a complete octet slash full shell, orbitals, whatever you want to call it. Whereas alkali metals and halogens are most reactive because they're the closest to completing their orbitals. They're both one electron away. Alkali metals by losing and halogens by gaining an electron. Metals, valence electrons are loosely held to atoms due to low ionization energy. So this is basically saying like how likely does it to like give up its electron to become stable, like the energy, I guess, to remove an electron. And electrons in previous shells are shielding electrons from the nucleus slash charge. So small negative charge is kind of lost in a sea of like closer, stronger negative charges. That's kind of what I like to think about like shielding is that it's shielding the outer electrons from the like positive charge of the nucleus. And this makes them good conductors, because their electrons are loose and they're able to move around a lot. They can move that charge around. They are lustrous, high melting point, high densities, and are malleable. And transition metals have multiple oxidation states. So they're kind of like loose. They aren't too picky about how many electrons they have, I guess. Non-metals, they are in the upper right slash right of the metalloid line, so over yonder. Um, they are dull, poor conductors of and their valence electrons are kept tight or kept inwards, and because they want to fulfill their orbital, and they have a lot of negative charge and a lot of positive charge, so they're highly attracted to one another and they're brittle. Metalloids are kind of like the in-between um, metals and nonmetals, and they vary wildly in their properties. Alkali metals are super reactive, as I was saying, because especially like as you increase N or move down, just because they're not really attached to the valence electrons. Um, as frequently because they want to lose an electron in order to complete their octet. Alkaline earth metals, same thing, slightly smaller atomic radii. They can easily lose two electrons to become divalent cations to obtain their octet. Chalcogens are six valence electrons. They're sort of reactive. They have small atomic radii, high electronegativity, and are typically toxic, except for oxygen, because obviously oxygen is really important for like makes up water. It's one of the two atoms that make up water. So then you have halogens, highly reactive because they have seven valence electrons, really close to completing that octet. Um, they are typically in gaseous, liquid, and solid phases, so they're kind of like all over the place. Then you have noble gases, which have eight valence electrons. They're also called inert gases because they're satisfied, so they don't want to react with anything. Then I have some of the properties of the elements. So, as you move from left to right, you're adding more protons and electrons, just as a general rule of thumb. So you're increasing attraction, from the protons to, the, electrons. Remember, like Coulomb's law, right? It's the absolute value, right? It's like in the numerator, you have like your two charges, whether it's positive or negative, over like your distance. So, yeah, just like as you increase the charges, but you're not increasing the distance at all. So you just make it increasing electrostatic attraction, increasing the force of attraction. Effective nuclear charge, or ZEF, as I like to say, Z, remember Z being the protons, is or sorry, like the symbol for protons. Um, You also always like frequently you see it referred to as the a measure of electrostatic attraction between electrons in the valence shell and the nucleus. So it increases as you move from left to right. Because remember from Coulomb's law, as you're not increasing a distance because like the shells are staying the same, but you're increasing the charges, so the numerator. And then as you move down a row slash period, the principal quantum number, or n, increases. Because the valence electrons are now further from the nucleus, remember, so you're increasing that denominator, but you're keeping the charges the same. Like, yeah, there's less attraction. There is increased shielding and decreased F. And then elements strive to complete an octet, just as a general rule of thumb. Not all, but most. It gets a little tricky once you move past the third row. Um, Here we have atomic and ionic radii. So here I just like kind of marked this is left, right, top, bottom of the periodic table. So atomic radii, its definition is that it's one half the distance between two atom centers when they're like in close contact with one another slash touching. So over here I have two electron clouds, which are like the orbitals of the electrons in the nucleuses. So the center would be the nucleus. So the distance between like essentially the two nucleus. So it's like half. So like the distance you can think of as the diameter between the two centers, and the radius would be half of that distance, as just as it is in a circle. So it increases as we move from top to bottom because we're adding more protons and electrons, so more shells, and it decreases as we move from left to right as the attraction slash Ceph score increases. Because remember, we're increasing that charge, we're not increasing that distance in Coulomb's law. Um, yeah, electrons are more attracted to the nucleus because we're adding more negative charge and more positive charge. Ironic radii are a little more tricky. It's like thinking about like whether an atom needs to kind of like gain an electron to complete an octet. So for nonmetals, or whether it loses electrons to achieve an octet metals. And then the second step is like for nonmetals, that are closer to the metalloid line. Remember the metalloid line is like over here. This would be like the non-metal side where I just like have green for like phosphorus. This would be closer to the metal side, aluminum, for example. Uh, Basically, like nonmetals closer to the metalloid line are larger because they gain more electrons. So it'd be like have a larger ionic radii than fluorine, where metals closer to the metalloid line are smaller because they lose more electrons. So aluminum would have a smaller ionic radii than magnesium, for example. Ionization energy. This is essentially saying like the energy required to remove an electron. So, the more favorable it is to remove an electron, the lower energy required to remove said electron. So, like the lower ionization energy, the better. The higher, that means that it's like um more stable. It doesn't want to leave. I guess the electron doesn't want to leave, so that means that it's like close to achieving its octet. So it has like 7 electrons. Whereas if it has a low ionization energy, it has 1 electron. Kind of. So, the left side requires less energy due to them like wanting to lose an electron to achieve an octet. Well, the right side is closer to the octet, so losing an electron would make them even further from their goal slash unstable. And the bottom is lower, like moving down from top to bottom due to the electrons being further from the positively charged nucleus, so there's less stuff. Remember, if you're thinking back to Coulomb's law. Our old friend Coulomb. You have charge, charge. Yeah, that's not. And then R squared is like your distance between the charges. Yeah, just because you're increasing the denominator, so like there's less electrostatic force. It is endothermic because in order to remove the electron, you need to add energy. Um, The first ionization energy is typically less energy because you're going from something that is neutral to a positive charge, whereas the second ionization energy has higher, requires more energy to remove the second electron because you're going from an already positively charged atom to something that is has 2 plus positive charge. So it's very unfavorable to remove something to create, basically make something more positive. Electron affinity. This is essentially saying how much the atom wants on another electron, so how favorable it is to become an anion. So this kind of goes back to whether or not it is closer to completing the octet if it has 7 electrons or 1 electron. So if it has 7 electrons and you add an electron, that essentially is really favorable. So it has a high electron affinity, so it really wants that electron. And it's essentially saying like how much energy is released when the atom gains an electron. So typically it's exothermic. Oh, some of the metals can actually be endothermic, like especially like francium and the larger one, just because it really doesn't, since that puts it actually further away from completing its octet. Um, yeah. Then we have electronegativity, which is probably one that you've heard before, just because it's like really common and like popular. Electronegativity is the attractive force an atom exerts on an electron. So when in a bond, or how likely the electron is found near its orbitals or nucleus. So if you have something like fluorine, for example, fluorine highly, highly electronegative, like the electron has a very good chance of being found closer to fluorine than, let's say, like it is, let me make this a different color, like hydrogen, which has a much smaller, um, like electronegativity. So it's the electron is less likely to be found, within hydrogen. Um, yeah. Basically, this also tells you, like, when you're looking at electronegativities, the difference between the two, whether it will be an ionic bond, so electron completely leaves one atom to go to another, which is typically found between nonmetals and metals, like salts, for example, like NaCl or sodium chloride, which is also known as table salt, or curvalent, so that means the electrons are shared. So like that could be something like I don't know, like hydrogen chloride. Like we'll just like see a lot, especially like if it's between like carbons and like hydrocarbon bonds. Yeah, that's kind of all I have to say about this, the periodic table. Let me know if you have any comments, questions, concerns in the comments below. And thank you for listening to me talk, and I hope you have a good rest of your day.